Good day, class. This is a continuation of my lecture on ductility, but this time we focus more on how ductility is measured in terms of curvature. So for or from the elementary strength of materials, I already defined to you what uh, the curvature phi is all about. Okay, so this is simply the moment divided by the flexural rigidity uh, EI within the beam, okay, within the entirety of the beam length, and can be measured particularly on a section uh, by section basis, okay. So you can take the curvature of a beam, say this beam here. If you take a look at the elastic curvature or this elastic curve of a simply supported beam, you can take this curvature P by defining, okay, the angle subtended from both ends in terms of this phi here, okay. So this is now equivalent also mathematically as the rate of change of the angle theta with respect to x, where in the angle theta are the, okay, angle subtended by the tangential line coming from these 2 points and B. Okay, so if we take the rate of change of this angle defined by a differential x, okay, so the x here is defined in terms of the distance from the left point or left support to the right support, then curvature is also uh, defined mathematically in this manner. But let's talk of a more simpler definition in terms of simply the moment divided by the flexural rigidity. Okay, if curvature is defined as the rate of change of the angle theta, we can say that the radius of curvature is simply the reciprocal of curvature. Okay, so the reciprocal of the radius of curvature is actually your curvature P. So these two here are reciprocals. Okay, so phi is actually equal to 1 over r, or r is simply equal to 1 over phi. Okay, so this rate of change of the angle can also be defined in terms of this rate of change of d theta with this differential strip dx uh, measured originally, no, from this straight beam, then going to this curved beam here. So in reinforced concrete design, the ductility of the section is made by allowing a 25% reduction on the steel. So we know that raw max is actually 0.75 of raw balance. Okay, so we have here 0.75, which is actually the factor of safety I'm talking about. Uh, the reciprocal of 0.75 is 1.33 to give way to a uninsured ductile failure. Okay, so because of some errors in the computation or in the dimensional characteristic of your beam, and some property errors of your materials, so we need to allow a factor of safety which is 1.33, limiting your raw maximum as 75% of your raw balance. Okay, so from this figure, we can come up with some equations, no? considering the three behavior or stages of beam behavior, starting from the uncracked elastic stage, the cracked elastic stage, and the cracked inelastic stage. So for the uncracked elastic stage, where the cracking stress is less than the flexural stress, okay, so we take note that your cracking stress is not yet reached by your flexural stress at the tension side. So T here has something to do with the tension side, normally at the bottom of the beam for simply supported beams. So as soon as this stress exceeds your cracking stress, then your beam will start to crack, and your beams will stay in an elastic behavior until such time that the fibers will no longer be able to rebound elastically, and it will go further to the crack in elastic stage, where cracking defined by the width of the crack will therefore be increasing, no, from a certain value to the failure value, okay. And this cracking can only be continuous cracking can only be controlled by the presence of steel, okay, steel reinforcement that will hold the propagation and widening of the crack into a limit, uh, thereby putting some ductility and strength in order, no? So without the steel, then your beam will behave in a brittle manner. So to take a look at these stages of beam behavior, I'd like you to look into the location of this neutral axis, wherein this beam section are converted into the uncracked elastic section, and these are transformed sections. These are not actual sections, these are transformed sections, but these are made in such a way that we can realize that the neutral axis, by the rule of balance, okay, balance uh, geometry, or balance uh, plastic strength, would mean that at the uncracked stage, your neutral axis favors more on the location of the steel, the tension steel. Okay, so these are tension steel. We disregard first compression steel. It favors on more the side of this tension. Okay, so these are the tension fibers and the compression fibers. So as soon as the portion of concrete here cracks, why? Because of the exceedance of the cracking stress, then your neutral axis will shift, favoring the compression side. So it will actually go up. So this now your neutral axis is stage 2. Okay, so this is stage 2, this is stage 1. And more so upon looking into the scenario wherein the beam will behave inelastically, then your neutral axis will again move, favoring again more on the compression side. So the area of this compression concrete actually reduces, no? Such that the strength of this is dictated by the balance contribution of forces on the tension and the compression. So here, the balance strength has not yet been defined in such a way that your steel does not behave uh, to resist tension yet, because this is an uncracked stage. While at this point, the steel already behaves, but still on the elastic range. Okay, the elastic range. So elastic means your steel has not yielded here. As soon as the steel yields or exceeds yielding, then this stage here is the will give you an inelastic uh, distribution of forces, and by using the equilibrium condition, balancing the effect of your compression concrete and your tensile steel here, uh, your neutral axis will be defined in terms of equilibrium, not in terms of the geometry of your section. Okay, so we can take a look at this stress strain distribution on the first and second and third stages. And if you look at the first stage here, you take note that your epsilon CU is very far from the ultimate crushing strain, which is defined in the ACI as 0.003. And in this at this point, this is still elastic. So your neutral axis at this stage is at the bottom, no? As shown here also in your behavior, upon which reaching the limit for the crack elastic stage, it will shift a little bit going to the compression side. Okay, so which now show, of course, there's a slight increase in your concrete compression strain, but still below 0.003. And as it reaches 0.003, we expect your epsilon y to reach also your yield strain. Of course, we are talking here of a balance strain condition in stage 3. So for the stress distribution, we take note that all the balance parameters here are simply converted into the balance stress block depth AB. Okay, that will describe or define your compression. Okay, so at the stage 3, I'd like to take note that stage 3, your stress will no longer be a triangular stress block, but rather a parabolic stress block, which can be represented by Whitney's rectangular stress block. So remember that the Whitney stress block and the parabolic stress block are just the same. No? The parabola here, defined by Whitney on his experiment, is simply a mapping or transformation by way of solving your K1, K2, K3 parameters. Okay, so these are the stress block parameters, which is also defined uh, in terms of PCA stress block. Okay, so K1, K2 is actually your 0.85 in your Whitney, and sorry, K1, K3 rather. Okay, so your K1, K3 is actually 0.85. I think beta 1, yes. And your K2 is actually beta 1 over 2 in terms of your uh, witness parameter. Okay, so these are now the equivalent parameters in your witness distribution. So take note that the location of the neutral axis is determined differently from elastic and inelastic, and we can observe it by going back to this figure here. So the elastic stage on crack behavior can now be represented by this formula, and I wouldn't like to go further on the derivation, but rather I just want to show to you how the location of the neutral axis are obtained. Okay, so YT here's your KD, which is simply an exercise using the Varignon's theorem. Okay, so for the elastic stage crack stage 2, okay, still this is a summation of moment of areas Varignons, and for the inelastic stage 3, no longer an exercise of moment of areas, but rather an exercise of the equilibrium condition. Okay, so for at this particular point, I'd like to fast track my discussion and talk about what ductility ratio is all about. So this ductility ratio is simply defined as the ratio of the ultimate curvature with that of the yield curvature. So when I talk of ultimate curvature, I'm talking here of what? My ultimate strain. We know that curvature is simply strain all over distance from the neutral axis. So this is simply measured from NA. So if we are talking of ultimate curvature, this must be epsilon Cu. And if we are talking of ultimate curvature, your Y here will simply be what? Defined maybe, no? Maybe in terms of the limit, and that limit can actually be your C balance, no? So this is at the balance condition. Okay, okay. So if we now take a look at here, so C is defined in terms of this. So this is simply in terms of 0.003, our ultimate crushing strain. This can actually change depending upon the code you want to use. And your Y here, your C here is actually your value for uh, the point upon which your C is equal to T, and that is defined in terms of the yield, no? Okay, the yield strain. Okay, so your KD here is on the elastic crack. Okay, this is the elastic crack, while your ultimate, okay, so if we take a look at this formula, this is your yield and this is your ultimate. Okay, your ultimate curvature will have to be computed on the basis of this equation. Okay, so that's how to solve for the ductility ratio. Perhaps we would like to have some exercise on this, maybe a problem, particularly on how to solve your curvature phi. Okay, so that's it for a moment curvature relationship. I'll see you on the next topic. Thank you very much for listening.